Hello, everybody. Um, Here I am to present you some approaches based on artificial intelligence for mapping forest disturbances on the basis of remotely sensed data. My name is Gerardo Chirici. I teach remote sensing and forest inventory at University of Florence. I'm the head of the Laboratory of Forest Geomatics, which is also a member of the Copernicus Academy. But this uh, project is developed in cooperation with many other researchers, the University of from University of Molise, University of Tuscia, from ISPRA, which is the Italian Environmental Protection Agency, and the Italian Society of Silviculture and Forest Ecology. So some basic information regarding forest resources in Europe, which are increasing. Moving from 1990 to 2015 on the basis of the last State of Europe's Forest, which is the report developed by the Interministerial Conference on the Protection of Forests in Europe. We have a yearly uh, increment of the forest area, which is around 0.5%, and also an increase of the growing stock volume, which is the volume of the wood in the forest area, which is even more, so 1.6% yearly. So forest resources are increasing, even if we are using part of these resources for wood production. We remove approximately 500,000 of cubic meters yearly. We do this in different way because, as you can see in this map, which is the ratio between the removals on the basis of the increments of the wood volume. As you can see, we are removing much more wood in central and boreal areas, and we remove a little bit less in Atlantic and Mediterranean regions. So it is essential to monitor wood removals. It is, and this information can be derived on the basis of remotely sensed data. So let's give a look to some very simple and background information. What is the what happens to vegetation, to a vegetation index that can be calculated on the basis of remote sensing of remotely sensed data when we clear cut an area for producing wood. As you can see, we start from an undisturbed forest, then we do the clear cut, so we are removing the vegetation. But after the clear cut, we have a growing, a regrowing, a regrowing phase of the vegetation. So the new generation of trees are growing up, and also the vegetation index is regrowing after this period. After a certain number of years, more or less the spectral signature of this clear-cutted area is more or less the same as before the clear cut. So we are recovering the vegetation. On the basis of this simple information, in literature, we can see that we can derive two basic approaches for mapping, for automatic mapping forest logging, so clear-cut area. The first generation of approaches was developed when large data set of remotely sensed data was not yet available. So basically, we use just two images first and after the disturbance to get this information. But then these changed because we started to be able to work with large number of remotely sensed data, because now they are all freely available online, both from NASA, from from ESA, and so on. So we are able to develop what we call the trajectories approaches. So we are studying the spectral trajectories across the years. So using a lot of dense time series analysis approaches. Some approaches were developed also on a global level, following these trajectory approaches. So this is the famous map coming from Hansen et al. In 2013, and then we have some updated versions in 2015 and 2018. But basically, they developed this forest disturbances map across the whole world. This was done on the basis of Landsat information. We started a lot of these very important effort, but we found that these global maps have some errors, big problems in Mediterranean conditions. So we prefer to develop our own approaches in it. Again, in the first phase of our study, we always study the spectral signature in undisturbed forest, and then after the clear cut, and then the recovery of the vegetation after the clear cut in comparison of undisturbed forest. So this is a typical distribution of pixels in a vegetation index. This is the NBR, so the normalized Barn ratio, which is a typical vegetation index used for forest disturbances approaches. So you can see the distribution of the values is the same after and before the clear cut. While in a clear cut area, we clearly see the distribution before the cut, and then we have a very dramatic change in the spectral signature after the clear cut, and then the recovery start just after that. So we are able to develop these kind of approaches to automatically map. So this is a first approach that we developed across the whole Italy. So it is the clear-cut map of all clear-cut in the period 1985-2018 on the basis of Landsat data, because of course we have to go back to 1985. But here, these are yearly maps. Now, what we are trying to do now, and this is the basic information that I want to present here, is that moving from traditional remotely sensed data Landsat and then Sentinel-2, which is much denser information than Landsat, because we have, of course, 2 satellites. Now we are moving to very dense constellation, such as this new PlanetScope project, which is more than almost 150 microsatellites. So we are able to have a revisitation time that is daily. So we have high resolution imagery daily. So this approach is the basis for developing this artificial intelligence approach, which I'm very briefly try to explain here. So on the basis of the analysis, as soon as a new PlanetScope imagery is available, we simply classify if a pixels is cut or not on the basis of a simple threshold. This is what we call penance reward approach. So as soon as a new image is available, we give the possibility to increase the reward if the clear cut is still there, or a penance if we are not able to see this change anymore. This is typical when we have cloud cover, because cloud cover is always a tricky point. So here we are not removing clouds, but the algorithm automatically see that the clouds is something that is not permanent in the very dense time series. So this is what we are looking for is a kind of almost an information that is available just after the clear cut. So we are able not just to produce one map for 1 year, but we are able to produce a map with a daily approach. So what we call a near real time. So we are able to date each single clear cut. Of course, we need some field truth to calculate false positive, false negative, and true negatives in order to assess the of our mapping approach. So this is what we are developing. So this is the time series of a planet scope imagery on 1 year approach. So as soon as new, and this is the accuracy. The accuracy is calculated here through the Matthew correlation coefficient. So as soon as new planet scope imagery are available, as you can see, the accuracy of our maps grows up. But we are able to reach a very good accuracy in a few months. So very briefly, some conclusion. We can use Sentinel-2 in combination with Landsat to operatively use automatic approach for yearly detection of clear cut, so one map per year. We can use PlanetScope imagery to automatically generate maps in near real time, and on the basis of a first paper we have in publication, we calculate what we call the mean time lag. So we are able to produce a highly accurate clear cut map after 7 days after the clear cut on the basis of PlanetScope imagery. Of course, to do this, we absolutely need a very good forest mask, which is something that is tricky because we know that we don't yet have an official high resolution forest mask for Europe, and we don't even have it in Italy. So this is very important. If we don't have a forest mask, we cannot create forest disturbances analysis. Um, what we are working on is on continuous cover cut, because what we can see from satellite imagery is clear cut, but what we call continuous cover cut, so other approaches in forest management can be hardly detected on the basis of remote sensing, but we are working on that.